Hello everyone, and welcome to your third Advanced Swift tutorial. In this tutorial, we're going to be talking about Swift's Hashable protocol, along with just hashing in general as it relates to programming or computer science. Now, hashing is used basically across all programming languages to have some kind of way to quickly look up a particular value. And this is used in Swift for dictionaries and sets, but anything that you want a O of 1 or a fast lookup to a particular object to see if it exists or not in a set or dictionary in our case, then you need to implement Hashable, or you need to have a hash function to do so. Now, what is a hash function? Well, let's just take an example here where we have this string of A. We'll hash the number 1, and I'm going to just run my playground here, and we can see that I get some different numbers, and a hash value is basically just converting some kind of entity into a number. That is really what a hash function is. And here we can see that our string of A gave us this integer, our number 1 gave us these values over here. Note that 1 and 1, right, they are equal, and so they should have the exact same hash function. This is a very important concept of hashing, is that if two entities are equal, they must have the same hash function. If I go ahead and let me run this again, we can see that our values will actually change. I get a -4 whatever, then again my 1s will be the same hash value. And the reason for this is that every time we run our program in Swift, we will generate a new seed that our hash function will then use to generate an entirely different hash. So the hashes are stable across the run of your program, but they are not stable across different runs of your program. So why this is important is that you should never store a hash value on disk or user defaults or anything like that and then restore it later, because the hash value will be completely different the next time you run your program. So hashes really only work while you're running your program. All right, so let's talk about the dictionary or set example. So if I have a dictionary or set, let's talk about the set case, right? So a dictionary is just a case where we have the key and it is hashable, but a set is basically a dictionary that has the key and value are the same thing. And so the value that we're inserting into the set is basically also its key, and that value is hashable. So how might we make our own implementation of set? And this is a very naive implementation of what a set might look like, but it gives you the general idea. So let's say I wanted to hash the value of A into a set. So I have a set of strings and I want to basically add these strings into the set, and then I want to check later on if I already have these strings in the set. So how I might do that is I might do something like hash value, and then I would mod by the number of available spots in the set. So let's say that my set was first created and there's 4 possible places that I could put something in the set. This is somewhat of a naive approach, but it gets the concept across. So I might take that hash value and mod it by 4, and if I run this, we can see that I get the index of 3. So great, I can then know that, well, every time that I go to check on the hash value of A and I mod it by the size of my set, then I can say that it's going to go into this index. And this is great because if I later check this and I said something like set contains, and then I wanted to see if it contains A, well, the set is just going to take the hash value. It's going to basically do this same kind of thing again. And it would say, great, that's at index 3. It would look at that index, then it will check the equality of those two types. So it's going to say, is the string A equal to string A? If it is, excellent. That means that A is contained in the set. Now, this is different than if we just had an array, right? If we had an array, we would have to go through every single element in the array until we happen to find the value that may or may not be contained in the array, right? So if I put the string A into an array, I'd have to say, well, is it at index 0? No. Is it at index 1? No. Is it at index 2? Right? Ad infinitum until we find or don't find the value in the array. And so this is why sets and dictionaries are efficient lookup mechanisms for values in this way, because their keys or their values in the set cases they are using this hash value or hash implementation. All right, so where does this hash value thing come from? Well, most standard Swift types will already implement this for us. but we can go over to Hashable, which is the protocol that all these things conform to, right? So strings and integers, they all conform to the Hashable protocol, which inherits from equatable. So anything that is hashable must also be equatable. If we are implementing the hash function, we need to implement it using hash into, and then we also need to implement the equatable, the equality function as well. And then once we've implemented a hash into, we can call hash value, and that will give us back the hash value from our hash into function. All right, so what are some examples of this? Well, we'll start with the easiest case, which is an enum. And I'll just do a simple enum that is a yellow, green, right? So this is just a simple stoplight enum. And if I wanted to get the hash value of this, we can see that I actually just get it automatically. This is kind of a strange case because we didn't even say that we needed to conform to Hashable, right? So we really should need to say something like that, but Swift will actually automatically do this for you with all enum types. It will automatically assume that if there is no associative values with them, then we will automatically get hashable conformance. However, if I, let's say I have this different thing, and we'll make an associated type with this. So we have an associated value with our yellow, whether, let's just say whether a person stopped at the stoplight or when it was yellow or not. We could even have it for red, but you get the idea. This is not really the purpose of what I'm trying to do here. So let's go back to, if I was trying to use stoplight 2, this will actually complain and tell us that stoplight 2 it doesn't have this hash value function. That's because it doesn't conform to Hashable. And in this case, we actually do need to explicitly state that stoplight 2 conforms to Hashable. Now, once I've actually explicitly stated that conformance, it will work because the type here conforms to Hashable, right? So because bool conforms to Hashable, this will work. So if I had a type in here, though, that did not conform to Hashable, so let's just take a random struct case, right, where I have this struct A, and it doesn't conform to Hashable. This is not going to actually work because my struct A does not conform to Hashable. So therefore, stoplight 2 cannot conform to Hashable because, well, obvious reasons, right? So if you're going to get automatic hashable conformance, all of your types in the enum, including the associative values, need to be hashable. All right, let's move on to the struct case, and we'll call this just struct D. And we'll do a very simple integer and string here. Oops. And in this case, I just need to explicitly state that I conform to Hashable for this to work. So I can say I conform to Hashable and 0 and nothing and hash value. There we go. So all of that will work just fine, and we have a hashable struct, right? So the same rules apply to this as it did to the enum with associated values, is that basically as long as all the values that we have in our struct are hashable, then hashable conformance is automatic. All right, the last case that I want to handle here is the class, and there's a few kind of tricky things with classes as well. So let's make this little class called classy, and we'll take these same values that we had from our struct up here. We need to make an initializer for that, so int b is a string, and then self.a gets a, self.b gets b. All right, so now if I tried to conform to Hashable with this type, we would see that it should complain it as here that classy does not conform to the protocol equatable. And basically, classes in general will not automatically get hashable conformance because you actually have to be relatively careful. And in general, I would say avoid using hashable with classes in general, but we'll talk a little bit about why that might be the case. All right, let's fix this up by adding in our stubs. So we need our equatable conformance here. So to do this, we would say is the left-hand side's A equivalent to the right-hand side's A, and is the left-hand side B equal to the right-hand side dot B. All right, and then for our hash implementation, we need to implement the hash into function. To do this is very simple. We just use the hasher that is given to us, and we combine the values that we want to include. So we want hash for A and we want hash for B. And because both of those are already hashable, this all works fine, right? Both int and string are hashable values. All right, so let's go ahead and run this. I guess I really shouldn't get anything out of this, but let's go ahead and make an instance of this. So we can have 0, empty string, and hash value. All right, let's go ahead and run this. And one very interesting thing about this is that if we compare our struct and our class's hash values, you'll note that they are actually the exact same. And this is maybe a little bit odd, but it does make sense because basically the way struct, or our structy instance here, is going to hash them is basically the same way that we're hashing them here, right? It's going to combine A, it's going to combine B, and now you have its automatically generated hasher implementation. All right, so here, the important thing to note though is that because the hash values are the same, it does not mean that the objects are the same. And that is very clearly the case, right? Structy is a struct. It is not equal to classy, right? I cannot compare, I cannot equate these two entities together, and they're not going to be equal, right? So that's a very important thing to note, is that just because hash values are the same, it does not mean that the value type is the same, or the instances are the same. All right, so let's talk about how we can screw up our hashable implementation. So doing kind of your own hashable implementation is somewhat dangerous, and so anytime you can get away with just automatic conformance of it, go for it. Do not try and implement your own implementation unless you have a relatively good reason to do so. So let's, we're going to create a set here, and the set is going to be containing a bunch of classy instances. And we're going to loop over this 1,000 times. And then, so what are we going to do here? We're going to create a new classy instance, and we're going to pass the I. Oops. We're going to pass the I in from our for loop, and our string of B will just be empty. And then we're going to insert this into the set, like so. All right, so let's go ahead and run this and see that all is well. So good, we get that it ran 1,000 times, and we should get also that our sets count is also 1,000. So that worked correctly. All right, so now with that, how can we screw up our hashable implementation? Well, it is somewhat a little bit easy to do. So in this case, we're changing our value of A. Now, let's say that we are only going to ever check or equate the value of B. So in this case, our equality is really only hinging on the value of B. It doesn't have anything to do with A, but our hash implementation uses the value of A. Well, let's go ahead and run this and see what happens. So it might be successful for a little while, but at some point you will probably get this error. And we can see at the bottom, fatal error, duplicate elements of type classy were found in a set. This usually means either that the type violates hashable requirements, which is what we have here, or that members of such a set were mutated after insertion. We'll talk about that second one in just a bit. But this first one is the problem that we have, right? So very important rule with Hashable, or your hash implementation in general, is that if you are hashing a value, that value must be used in the equality. So anything that you hash here, so in this case we're hashing A and B, those two values must show up in the equality, right? So for this to be a true working implementation of hashable instance, basically the hash values need to be a subset of the equatable values. So we could equate other things in here as well. So if we had a third property, let's say it was C, we could still do a comparison to see that the C equals the C of the left and right side, and not include C in the Hashable implementation, and that would be just fine. Okay, so again, the rule is that your hash values need to be a subset of the equatable. It can't be the other way around, where that if you're inserting values into your hash, basically, the rule is very simple. If they show up in the hash, they need to be in the equatable. All right, let's see another example of where this could fail. So let's say that we took out, so instead of only comparing our B, we're actually only going to compare our A. And I want to show you a case where this can actually succeed just fine, and you'll be a little bit surprised that it does, perhaps. So we're going to run this. We see, wow, it worked. We added it 1,000 times. It was 1,000 times in it. I mean, didn't I just say that your hash implementation or your equals implementation needs to be needs to contain the same elements that are in the hash function, right? And yes, I did say that, and it is still the case. The reason that this works okay is because our B is just happily it's not changing in any way, and the A values are all unique. So if I change this so that all of a sudden my integer always stayed the same, but I could change my B, it didn't really matter. I could leave B the same if I wanted, but if I run it this way, we can see, oh, I ran it 30 times, but somehow it failed on this time, right? So it's kind of this weird thing where, because our hash value is changing, right? We were hashing B and B was changing, so the hash value is different. But at some point there was a collision, and we went to compare our A's with our two A values together, right? But they were equal values, but the hash values were different, right? And that, like I said before, breaks the hashable requirements. All right, let's undo this, and we'll keep our instance correct as it is here. But this time we're going to mutate one of the values on our class. So after we've added C to the set, I'm going to set a value of 0 onto C.A. Now, why is this going to be an issue? Well, because I'll wait for this to run, but basically our class, right, if I'm mutating values after I've inserted it, the hash that we initially calculated on insertion is different after I've changed the values, right? And we can see that when we got our fatal error, that that second part down here, which says, or that members of such a set were mutated after insertion, is exactly what's happening here, right? We change C, which is a member of the set, and now its hash value is completely different, right? Which is not really compatible with how we're using hash values. So this is a big no-no. One way to avoid this would be to make your class essentially read-only, right? So this would say that we can't mutate values, and so this would still be a valid use case for our class. Now, there's one further caveat with this, though, is that if, for example, I could declare all my properties in the class to be let. However, if I have, let's say, another class, right, and in this class we have things that can be changed, right, then we could really do something very indirect, and we could do this somewhere totally different in the program. It would be relatively difficult to even debug this scenario, but that's why it's dangerous. But we could have something like this where we're saying C.A, right, which is totally fine, but then maybe value on this other class is mutable, and we can change that. And because A is part of this hash function, right, well, now we've changed the functionality, or rather the hash function output of our class in total. So you have to be extremely careful with using classes that are hashable. You have to make sure that nothing can be mutable, or there's no mutable aspects of that instance. Structs are fine to use in this case because they will always be, if you try to mutate a value in a struct, you're just getting a copy of the struct. So once it's inserted into the set, for example, there's no real way to change the values of that set. However, the one caveat that I would give with that is that if you have a class that is a property of a struct, this could still be an issue, right? So if you're combining, if you have a class as part of a struct, then you could still change that class indirectly, right? Which would still technically change the calculation on the hash value as well. So in summary, avoid classes with Hashable. If you really have to for some reason. I don't know if there's some performance aspect that is out there that maybe would make this useful, but in general, it's just quite dangerous. And even if it works now, it just takes somebody else in your code base to change something to then break it later. So with that said, those are the two main things that I wanted to talk about in this video, which was that your hash implementation needs to anything that you hash in your hash function must be contained or compared against in your equatable, and that anything that you're using as a hashable entity can't be mutable. There shouldn't be any way to mutate values such that the hash function can then change as a result of that as well. All right, I hope you enjoyed this, and I hope this was helpful. I'll see you guys in another video. If you enjoyed this video, please subscribe to the channel, give this video a like, and share it with your friends. Ways to contribute and additional information are in the description. I'll see you next week.